Hello and welcome to our lecture 9, part 1. I'm so excited to welcome you back here. Today we're going to be talking about a topic that is as exciting as the one that we finished off last time. And last time we were talking about stellar explosions. So today, in part 1 of lecture 9, we're going to begin a couple of lecture series entitled Linear Oscillations. They show up everywhere. You know, if I bang on the table, don't try that at home, the table will vibrate. And those vibrations are made up of a bunch of oscillators coupled to each other. And if only there was a way to try and simplify this cacophony of different frequencies and sounds when we do that. And that's exactly what we're going to be talking about today. How to linearize complex systems and describe their behaviors in a tractable way, where all the different couplings can actually be taken care of. In fact, we're going to be breaking down these complex systems into eigenmodes and eigenfrequencies. We're going to separate the frequencies apart. We're going to separate the eigenmodes, what vibrates and in what kind of phase, also part. It might sound a little bit confusing right now, but you will see how it works. And there will be a lot of linear algebra, and there will be a lot of matrices. So get ready for fun, buckle up, and stay with me. So, linear oscillations, super exciting because they show up everywhere. More specifically, they show up in Goldstein 6.1, 6.5 are the chapters. So if you're interested in more detail, please take a look over there. Great. So suppose that we have a system. Let's plot its potential. So energy as a function of radius, or let's call it x. And we have a potential that looks something like this. So this will be V of x. And the energy of our particle will be sitting right here, given by the standard formula 1/2 x dot squared plus V of x. So here we have set mass to 0. Sorry, to 1. For simplicity, mass to 0, that would be photons, that wouldn't work. What we're interested in is oscillations of the system around the equilibrium point, because in order for oscillations to happen, there should be a returning force that brings us to equilibrium. So this, for instance, would be the equilibrium point, x naught. And let's try and make the notation more general. So our generalized coordinate will be q, and our equilibrium point would be q naught. So what does it mean that the oscillations are linear? It means that we're considering small deviations. So in fact, if we consider small deviations from the equilibrium point, then linear approximation would be good enough to describe its behavior near the equilibrium. This marker is really dying. Luckily, I have a few more along the way. So there can be two situations, as we already mentioned. One situation is if we have an unstable equilibrium point. In this case, the potential force, the minus dV dx, will actually be pushing the point away from equilibrium, so the point will fall off and not going to come back to the equilibrium where we started out. If we consider potential that has a minimum, then if we were to displace the particle up, it would come back down. That's because it's the minimum. So that will be the stable equilibrium. And this is the one that we're going to be interested in. So let's try and take a look at an example of a system where we will linearize it and try and find its eigenfrequencies. So let's write down the Lagrangian where we will go from x to q so that it's more general. So it would have the form of kinetic energy minus the potential energy. And one very important concept here is the equilibrium point. So what we're going to do is we're going to break down the coordinate into the equilibrium point plus the deviation. So equilibrium point q0 plus the deviation that we will denote as eta. And then our Lagrangian will look as follows. Let me demarcate boundary here. So our Lagrangian will look like L is equal to 1/2 eta dot squared, because if we plug in q equal to q0 plus eta, q0 doesn't depend on time, it's an equilibrium point, it's a constant, so the only time varying part is what will contribute to the time derivative. And then v of q we're going to represent as follows: v of q0 plus eta. All we've done is we just plugged in q inside of v. And this term, v of q plus eta, we're going to represent as follows. So we're going to say that it's equal to v of q0 plus, so let's do Taylor expansion around q0, plus eta times dv dq at q0. So that will be the linear term proportional to the derivative. And then there will also be the quadratic term, 1/2 eta squared d2v d eta squared, also at q0. So at equilibrium point, we will have a few things happen. First of all, we will have that dv dq of q0 at q0 is equal to 0. Therefore, this term goes away. This term is a constant, so it doesn't really matter. We can rescale our potential energy, add a constant, subtract a constant. So without loss of generality, we can throw away this term as well and just set it to 0. So therefore, if we retain the lowest order terms in our linearization, the ones that actually cause the oscillation itself, we're going to retain this term. And here, an important parameter is the second derivative, which we will denote as k. So what we're going to get in the end is that our linearized Lagrangian will look like L equals to 1/2 q dot squared. Oh, not q, of course. We've switched to eta. So it will be eta dot squared. Eta dot squared minus 1/2 k eta squared. So that is our linearized Lagrangian. Awesome. So what are the equations of motion? Well, the equations of motion are, as usual, we're going to set d dt of dl dq dot, or in our case, it will be dl d eta dot, right? Because now eta is our new variable, essentially, right? This is what we switched to. So this will be dl d eta dot, and that is going to be equal to d dt of eta dot, so that will be equal to eta double dot. And so this, at the same time, is going to be equal to dl d eta, which is equal to k eta. So that is our equation of motion. So, and this is really the Lagrange equation, or Lagrange equations. So eta double dot is equal to k eta, with, of course, the minus sign, which I forgot over here. So our solution will be that eta is equal to some constant times minus I omega t. And what's important is that omega here is equal to square root of k, right? Eta double dot is equal to minus k eta, so omega is square root of the prefactor. So that is our oscillation solution for the linear system. So let us consider an application of this to a Keplerian potential. So let's look at an example 1. So here our potential is going to be given by the gravitational plus the centrifugal one. So that is our effective potential, the one that we derived previously. So what is our equilibrium point? So the equilibrium point is where the potential vanishes. The potential derivative vanishes, so the force vanishes. So dV dr is equal to 0. And here, therefore, we will have that dV dr is equal to gm over r squared minus L squared over R cubed. And all of that is going to be equal to 0. And from here, we're going to get that our equilibrium point is equal to, so one of the r's, R squared goes away. So R is equal to L squared over Gm. So that's our equilibrium point. So what is going to be the value of the spring constant, K? So the value of spring constant is V double prime evaluated at 0. So the second derivative will be minus 2 gm over r cubed, right? Plus 3 L squared over r to the 4th. And here what we can do is we can plug in this right into here, right? So we already have L squared over R cubed. So that means that L squared over R cubed will be equal to GM over R squared. So we're going to plug that in here, and we're going to get in the end minus 2 plus 3 of GM over R naught cubed. So that will be our answer, simply GM over R naught cubed. And therefore, from here, we're going to get that omega is equal to square root of k. Let us actually go over here. Omega is equal to square root of k, which itself is equal to g square root of gm over r naught cubed. So that is going to be our omega. So what we can see that in this case of linear oscillations in the Keplerian potential, our omega is equal to the Keplerian frequency. As we have seen in problem set 2, this is precisely the property of the Keplerian potential that ensures that the orbits that are not circular are going to be closed in the potential. That is precisely because the radial oscillation frequency, which is what we just found, is equal to the orbital frequency. So that's why when the two are in the same frequency, then the orbit closes, because both oscillations come back in the same phase when it's time for a new orbit. What is going to be next? Well, next we're going to go ahead and see what happens to when there are multiple degrees of freedom, not just one, but multiple degrees of freedom, namely multidimensional oscillations. I'm going to see you then. Hello and welcome to part 2 of lecture 9 on linear oscillations, and now we're going to be talking about multiple degrees of freedom. So we're going to be talking about many degrees of freedom, or when our Q's are many, from 1 till n. So we have n generalized coordinates. So in this case, our kinetic energy is the sum of kinetic energy contributions from all of the degrees of freedom. And in general, because they can be crosstalk between different degrees of freedom, it's not a diagonal sum of m1 q1 squared over 2 plus m2 q2 squared over 2 and so on. It is actually a bilinear combination of various degrees of freedom. So we will have a mass matrix that is multiplied by some combination of velocities, qi dot times qj dot. And here, Einstein's sum over different indices is implied. Well, great, that's kinetic energy. We also will have a similar expression for potential energy, but so far we will write it in the general form. You will see how we'll reduce it to this bilinear form in just a moment. At equilibrium point, our potential will have to have all of its derivatives 0, because it has to be a critical point, not along just one, but all of the n generalized coordinates. So at equilibrium point, dv dqi is equal to 0 for all I. And from here, we can compute what is the equilibrium point itself, q naught I, in full analogy with what we did over here with the linearization for one-dimensional case. So now that we have done this, that we know what the equilibrium point is, we can introduce the splitting between the equilibrium point and the deviation from the equilibrium point, exactly like we did before. So we will write down each of the n generalized coordinates as a sum of the equilibrium value of that generalized coordinates plus coordinate plus the deviation from that. And we're going to linearize in eta I. So, for instance, what we can do is we can write down that mij is going to be equal to mij at the equilibrium point plus terms which are of order linear in eta or high order. So this O with the 2 underlines, it's the big O, means that it represents all of the terms of that are of the form some coefficient that's a constant times eta plus another coefficient times eta squared plus and so on, higher order terms in eta. So if we only care about terms that don't depend on eta, as we will see in a sec, then we will only retain this term and we will drop all the higher order, first order and higher in eta. Similarly, we can, and from here we can use this in order to linearize the expression for the kinetic energy, where we would write it down as 1/2 of mij of q0i, that's the equilibrium value, times eta I dot times eta j dot, plus terms of order eta dot to the 3rd power, because these terms here, they contribute only at most the 2nd power of eta dots, and then everything else coming from the corrections as mij deviates from its equilibrium value, that will contribute only to higher order terms, which we actually will neglect when linearizing the system. So that is our expression for kinetic energy, and we will slightly rewrite it in the following way. We will denote this coefficient in terms of the Tij matrix, which will be constant, and it will give us the kinetic energy of the system. That's what we're going to be working with. So that is our kinetic energy. So now we can do exactly the same, but for the potential energy. So the potential energy V is given by its formula right here, but we're going to now Taylor expand it around the equilibrium point, Q0I. So it will be the value of V at the equilibrium point plus the linear term dV d eta I at Q0 times eta I plus the second order term 1/2 d2V d eta I d eta J also at the equilibrium point times eta I eta J. Plus we will have to include the terms of order of eta cubed or higher. So that is our Taylor expansion of V, and first of all, at the equilibrium point, we can say that this is equal to 0 because of that, and we can now finally write down what is going to be our Lagrangian, and this is equal to T minus V, and that will be equal to 1/2 of Tij times eta I dot eta J dot minus Vij eta I eta J. Plus, in general, you can have a term Aij eta I eta J dot. So this is more general form that we might consider in some of the problems. So here in this formula, Atij is nothing but the second order derivative with respect to eta I dot eta J dot at the equilibrium point. And Vij is similarly the second order derivative of V with respect to eta I and eta J also at the equilibrium point. So we can refer to this loosely as the mass matrix and to this as the K matrix. Because in the one-dimensional case, this would reduce to mass and this would reduce to K, to the spring constant. So in the problem set 3, what you're going to have to do is you're going to have to find the mass and K matrices, Tij and Vij. Let us now, in the next part of this lecture, consider an example of a double pendulum and how we can find these sort of matrices. But before I leave, there are a couple of comments that I would like to make. One thing is that these matrices are constants. They do not depend on the velocities of the coordinates. So you can think of them as the Taylor expansion coefficients or Taylor expansion matrices of Taylor expansion coefficients that are evaluated right there at the equilibrium point, and the only dependence on coordinates comes through the expansion. So there will be eta I eta J dots and eta I eta J over here, but these two are constant matrices. The same way as this matrix is also a constant because it is evaluated at Q0. So that is a really important, crucial concept in linearizing the systems like we're doing right now. It will be super exciting. See you soon. Hello and welcome to part 3 of lecture 9. where we're going to take a look at an example of using the machinery that we just developed to linearize a system. And the system that we're going to consider will be a double pendulum. So, double pendulum, just like before. Is a pendulum with two segments. There is a regular pendulum with mass m1, and there is a second pendulum attached to the mass 1, such that the two can swing independently. So there are 2 degrees of freedom, and the equilibrium point is theta 1 equal to theta 2 equal to 0 when the pendulum is hanging vertically. So what are the types of oscillations, and what are their frequencies? This is what we're out to figure out. So let us try and write down the Lagrangian and linearize that. So for that, we will follow the algorithm that we followed previously. We will write out the kinetic energies of each of these masses, potential energies of each of these masses. We will then linearize those expressions as we did before by finding the Tij and Vij matrices, and then we will be able to construct the linearized Lagrangian that we will then be able to eventually solve. So x1 here will be given by L times sine theta 1, y1 will be given by L with a minus sign times cosine theta 1. And as a result, from here, we can write down that x1 dot is going to be equal to L times cosine theta 1 times theta 1 dot, and y1 dot will be equal to L times sine theta 1 times theta 1 dot. So here, what's important to understand is that we don't want to retain terms that are of too high order. The ones that will contribute to Tij, to the kinetic energy and to the potential energy to order higher than 2 in eta or eta dot, or in this case, theta or theta dot. So here, for instance, cosine of theta 1 around the equilibrium point will be basically a constant, equal to 1. And sine of theta 1 at the equilibrium point will be basically 0. So this term will be of second order in theta 1. So when we square that to plug that into the kinetic energy, this term will be of too high order. So we actually don't worry about that. So this term will be of order of theta dot squared, or theta squared. So we don't really worry about that. And we will set it to 0. This term, however, will be of order of theta 1 times L, right? L times theta 1. So we're going to retain that term. So what about x2 and y2? So x2 will be equal to L times sine theta 1 plus sine theta 2. And once we do the same thing for y2, we'll see that is cosine theta 1 plus cosine theta 2. And I'm using s and c in place of sine and cosine for the compactness of notation. As a result, we're going to get here that x2 dot is equal to L times theta dot 1 plus theta dot 2. And y2 dot is going to be equal to something that is of higher order than linear in theta, right? Because cosine, when we expand it, it becomes 1 minus theta squared over 2. So this is going to go down to essentially 0 or a constant. And so we're going to be essentially just left with the x2. And let me draw a demarcation line so that we're not confused where different things are. Apologize, this is a little bit tangled over here. So let us write down what the kinetic energy will be then. So T is going to be equal to m1 over 2 times L squared theta 1 dot squared plus m2 over 2 times L squared times theta 1 dot plus theta dot 2 dot squared. And all of that is going to be equal to 1/2 of Tij theta I dot, oh no, square, times theta I dot times theta j dot. So now let us try and find the Tij matrix. So how do we do that? Well, Tij matrix is d to t d theta I dot d theta j dot evaluated at q0, right? So that will be evaluated at theta 1 equal to theta 2 equal to 0, right? So what will that be? Well, let's take the L squared off of here, and then here we're going to have d to t d theta 1 dot squared. So that will have, we will be left with m1, and there will be also contribution from m2, right? m1 plus m2. Now let's do this one. So we're going to have m2 over here. And here, this will be a symmetric matrix, right? So this will be m2. And here we will have the second derivative with respect to theta 2 dot. So that will give us m2 as well. So that will be our mass matrix, which we can rewrite in the following way. We will introduce m, which is given by the sum of m1 and m2, and the matrix itself will reduce to 1 mu mu mu, where mu is given by m2 over m. So then let's do exactly the same thing for the potential energy. So what is the potential energy? That's the sum of potential energies for mass 1, m1 gy1, and plus the potential energy for mass 2. So what are those? It will be minus m1 gl cosine theta 1 minus m2 gl times cosine theta 1 plus cosine theta 2, right? Because we need to sum both of them up. So that will be our potential energy. And if we expand the cosines, here we will say that the cosine is cosine theta is approximately 1 minus theta squared over 2. So if we're going to do that, so let's write this down. We will be able to factor out GL from here, right? And we will be using this expansion for cosine. So let's keep track of the terms that depend on thetas. So from this term, we're going to get m1 with a minus sign times theta 1 squared over 2. So we're going to get m1 theta 1 squared over 2. From this term, we're going to have m2 times theta 1 squared over 2. So that will be plus m2 theta 1 squared over 2. I don't know why my hand tries to write theta 1. Times theta 1 squared over 2. Plus here we will have m2 times theta 2 squared over 2. Okay, so that is our v. Only the terms that depend on theta 1 and theta 2, plus there will be a constant term where we will have used the 1, which we don't care, plus there will be terms of order of theta cubed, theta 1 cubed or theta 2 cubed, which we actually don't care about either. So, or even higher, I think cosine only has even power, so it'll be of order of theta to the fourth. So we are going to ignore those terms as well because they're going to be at higher order than linear for our forces. So now what we're going to have is our K matrix of Vij, which will be the derivative with respect to theta 1 and theta 2 as evaluated at theta 1 equal to 0 and theta 2 equal to 0 as well. So let us take out GL like we did before, and let's try and compute what the components in this matrix are. Let me make it bigger. So d2v d theta 1 squared, we will have contributions from both of these terms, so it will be m1 plus m2. What about d theta, d2v d theta 1 d theta 2, which will be this term, and you see that there is no cross terms here, so it will be 0. By symmetry, this will be 0 as well, and here we're going to get that this will be simply m2. So this will be our K matrix, or we can write it out using the similar notation to this as MGL of 1, 0, 0, and mu. So this is just like that. Both of them are constant matrices. No variables. And as you can see, both of them are symmetric matrices, which is not surprising because we can always write down the Lagrangian, the kinetic energy and potential energy in a symmetric way, because the second derivatives are always symmetric for smooth t and for smooth v dependencies on the coordinates. So let us now move ahead and try and see what we can do. How can we solve this? And this will be done in the next section 4. Please don't forget to do the quiz, and I'm going to see you there. Hello, and welcome to part 4 of our lecture 9, where we're going to continue our topic of linear oscillations. And we are about to figure out what the equations of motion are. So how do we do equations of motion? Well, we write down what the Lagrangian is, and it is kinetic minus potential energy, or T minus V, or in the matrix form, it will be the Einstein sum of Tij times eta I dot times eta j dot minus Vij times eta I times eta j. As usual, the sum over repeated indices is implied. So how are we going to move forward from here? Well, we're going to write down what the kth momentum is, which is dl d eta dot k, and that is giving us the equations of motion, because d dt of pk is equal to dl d eta k. So we're going to get the equations of motion, which look like that: tki times eta I double dot is equal to minus vki times eta I, or written out in the matrix form, where matrices will have two underlines and vectors will have one underline, we are getting this equation of motion. T times eta double dot plus v times eta is equal to 0. So this is our equation of motion. How are we going to solve that? Well, we're going to look for a solution in the oscillatory form. We're going to write it down in the form eta 1, eta 2 is equal to amplitude vector a1 and a2 are its components, times minus e to the minus power of I omega t. If we were to take this and plug into that, then we're going to get the second derivative in time will give us a factor of minus omega squared times t, and the factor here will give us just the v itself, and all of that is going to be multiplied by a and equal to 0. This is looking like an eigenvalue problem, except it is not a usual one. So what makes this an unusual problem is what we have here is we have v times a is equal to lambda times t times a. But the usual eigenvalue problem would look like v times a is equal to lambda a. So this presence of extra t matrix is what makes this an unusual eigenvalue problem and more interesting. So how are we going to then move forward with what we had on the left over there? Well, over there we had a matrix that we can now massage, and we're going to plug in the solution in this form into that matrix. So what we're going to have is minus omega squared times ml squared times our matrix plus mgl times our v matrix. All of that is going to be multiplied by a1, a2, and is going to be equal to 0. Let us simplify this a little bit. Let's multiply all of that by mgl to the minus first power, and we're going to introduce omega tilde, which is equal to omega divided by g over L. So if we're going to do that, then this all becomes the following: minus omega tilde squared times 1 mu 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 plus this mgl will go away. We're going to get 1, so this becomes that, times 1 0 0 mu, and all of that is multiplied by a1 a2, and all of that is equal to 0. So what are we going to do with this? Well, let us collect the terms. So in the first term we're going to have minus omega tilde plus 1. In the top right term we're going to have minus omega tilde squared times mu. In the bottom here we're going to have this one plus 0 minus omega tilde squared times mu plus nothing. And in the bottom right we're going to have minus omega tilde squared mu plus mu. So that will be minus omega tilde squared plus 1 times mu. And all of that is going to be multiplied by a1, a2, and all of that is going to be equal to 0. So here let us consider an analogy. When instead of a matrix times a vector equal to 0, let's consider an analogy when mass times a equals to 0. And in this case, in order to have a that's non-zero, because we're looking for non-zero, non-trivial eigenvector, need to have m equal to 0. So here, in this case, the analogy is that to have a1, a2 that's non-zero, need determinant of this entire matrix to be equal to 0. And this condition is what's going to give us the eigenvectors and eigenfrequencies of the system that we are considering. And we're going to do that in the next section 5, which will be the last one. I'm going to see you there. Don't forget to do the quiz. Hello and welcome to the last part of lecture 9.5. Here we're going to figure out finally what the eigenfrequencies and eigenvectors are of our double pendulum. And we're going to do that by using the condition, the determinant that we obtained over here. So we're going to say that the determinant of the matrix that multiplies the eigenvectors is 0. And that is going to be equivalent to minus omega tilde squared plus 1 squared times mu minus omega tilde to the fourth times mu squared equal to 0. We're going to cancel out the mu's over here, the factors of mu, and we're going to get the following equation from here, that omega tilde to the fourth times 1 minus mu minus 2 omega tilde squared plus 1 is all equal to 1. Here we're going to get that omega tilde squared is going to be equal, plus minus is going to be equal to 1 plus minus 1 minus 1 minus mu divided by 1 minus mu, or equivalently it will be 1 plus minus square root of mu divided by 1 minus mu, or equivalently it will be equal to 1 divided by 1 minus plus square root of mu. So that will be the solution for our eigenfrequencies. Let us consider the limiting cases. So the limiting cases are, what if our second mass is equal to 0? Then in this case, we are going to end up with a single pendulum with the dimensionless eigenfrequency equal to 1. So this is single pendulum, only one weight. All right, so that's good. What about the other limit, mu equals to 1? Well, in this case, we are going to have 1 divided by 1 minus plus 1. So in this case, the finite frequency, omega plus, is going to be equal to omega plus tilde squared is equal to 1/2. So here we have twice as long pendulum, right? Because if mu is equal to 1, it means that all of the mass is in the second pendulum, so it's just a pendulum that is twice as long as the original one. That's why omega squared becomes twice as small. So let us try and find eigenvalues. And here we can do the following: minus omega tilde squared plus 1 times a1 minus omega tilde squared times mu times a2 equal to 0. So what we're doing is we're taking the matrix and we're taking the top row over here and multiplying it by the column. So the top row is this and that, and the column is a1, a2, and this is why we're getting this equation. So here we're going to try and plug in the expression for omega over to here, and we're going to get the following: 1 minus 1 over 1 minus plus square root of mu times a1. All of this is going to be equal to 1 divided by 1 minus plus square root of mu multiplied by mu times a2. So let's multiply this one such that it has the same denominator. So we're going to multiply it by 1 minus plus square root of mu. And we're going to get in the end minus plus square root of mu times a1 divided by 1 minus plus square root of mu. all of that is going to be equal to mu a2 divided by 1 minus plus square root of mu times mu times a2. So we can cancel out the denominators because they are the same in both cases. And we're going to get the solution for the eigenvectors in this following form, that a1, a2 is equal to minus plus square root of mu 1, and from here we're going to get that theta 1, theta 2 is going to be equal to c1 minus square root of mu 1 times e minus omega minus t plus c2 times square root of mu 1 times e to the minus I omega plus t, right? Because it's these. So this is our solution, which contains two sinusoidal components with omega minus and omega plus, and because this is a linear problem, any linear combination of these two will be a solution. These C1 and C2 are coefficients that are completely free. So let us consider two cases. I'm going to switch over here so that I actually squeeze into this board and don't start a new one. So let's consider the case of mu equals to 1. That is the same case as we considered here, but we have this weird situation that omega tilde minus is actually equal to infinity, because if we plug in mu equals 1 over here, you see that the minus version of omega gives us 1 over 0, so omega minus is equal to infinity. So how do we understand that? Well, in this case, we have two terms. We have the omega minus term and the omega plus term, and the omega minus 1 is equal to infinity, and the omega plus 1 is equal to square root of 1/2. What does it mean to have omega tilde minus to be equal to infinity? Let us draw the two cases. So for omega minus, we're going to have the perturbation be minus 1, 1 times the prefactor. So it means that one weight goes to the left, the other one goes to the right with exactly the same amplitude. So this is the omega minus eigenvector. And we'll also have omega plus eigenvector, where both of them will be going with the same exact amplitude, right? So this will be m1 and m2, so this will be omega plus tilde. And because m1 actually is equal to 0, right, all of the weight is sitting in m2, that means that the infinite frequency of oscillation of weight 1 really means that there is nothing to oscillate. So this mass 1 is going to oscillate left and right at omega minus equal to infinity. So this weight is oscillating at an infinite frequency, whereas weight m2 is sitting still. So that is what this eigenvector really represents. Whereas in this other case, m1 is really non-existent. It's just a rope, right? And so m2 is just acting as if it was an oscillator, single pendulum of twice the length of a single pendulum. So here, both of them will oscillate in sync at a frequency of omega plus, which is 1 over square root of 2. So this is the physical meaning of this system, and these two are the eigenmodes, where in one case, both weights are moving one way, and in another case, the weights are moving in opposite ways. So thank you very much for your attention. I hope this was fun and useful, and don't forget to do the quiz. I'm going to see you in lecture 10, where we're going to continue studying the linear oscillations. Thanks for your attention. Bye-bye.